In this lesson, we're going to be looking at transformations of cube root functions and solving cube root functions. So we're starting with a function, r of x, which is the cube root of 3 over 4 pi x. And this is representing the length of the radius of a sphere as a function of its volume. And the volume is being represented by x. An approximation of this is the cube root of 0.24x. So just to clarify what they did there, they went ahead and simplified that fraction, 3 divided by 4 pi, and got 0.24. And that is an approximation because it is rounded. And let's think about kind of what we did last time. We really don't like worrying about horizontal shrinks and stretches. It's a lot easier to deal with vertical shrinks and stretches. So kind of like when we had that the square root of 2x could be rewritten as the square root of 2 times the square root of x. Similarly, if we have the cube root of something times something, we can split it apart the same way. So cube root of 0.24x could be rewritten as the cube root of 0.24 times the cube root of x. Now, to find the cube root of 0.24, there's two ways to go about it. Remember that we found that a cube root could be something to the 1/3 power. So one way to do it is to do 0.24 to the 1/3. Or, if you go to math, the very fourth option is a cube root. And let's prove that you get the same thing. Now our instructions on the sheet say to round to 1 decimal place. So that would be 0.6. Now what is going to be happening to our parent graph if this is the transformation? Well, remember, that means we're multiplying our y values by 0.6, which would give me a vertical shrink by 0.6. Just like if we had had x cubed and 0.6x cubed, it'd still be a vertical shrink by 0.6. Now let's look at the graph. We'll have to make a table of our parent function, which is just the function y equals the cube root of x. Whoops, I'm sorry, they're calling that f of x. And let's think of some numbers that'll be easy to find the cube root of. Well, guess what? We can take the cube root of negative numbers. One way to work this might be to think about things cubed. If I took -2 and cubed it, I'd get a -8. So the cube root of -8 is -2. -1 cubed is -1. The cube root of -1 is -1. 0 cubed is 0. That's an easy one. 1 cubed is 1. And +2 cubed is 8. So notice we do have negatives and positives for both our x's and y's. So -8, its cube root is -2. -1, its cube root is -1. 0's cube root is 0. 1 cube root is 1. And 8 cube root is 2. Notice that we have a kind of a slanted graph here. If you turned it around, it almost looked like the cubics we researched last unit. So what's the domain of that parent function? Well, we talked about that we had negatives and we had positives, so it's all real numbers. our range, we also have negatives and positives. So it's also all real numbers. Now let's look at what happens when we apply that transformation. We're going to be multiplying our y values by 0.6. We could also look at the table, huh? So if you're going to put this in the calculator, let's see, it'd be 0.6, and then if you want to use the cube root symbol, there it is under 4, cube root of x. Let's look at the table and look at some of those common points we had had. Well, we had plotted -8, and it originally went to -2. This one's only going to go to -1.2. It shrunk just a little bit. -1 originally went to -1. It's going to -0.6. Well, guess what? I think, so this one went to -0.6, and 8 went to -1.2. If I multiply that by 0.6, we'd get a very almost symmetrical layout. Now this is the same shape, it's just vertically shrunk. So it's the same shape, what can we say about its domain and range? Well, they're going to be the same. So that's kind of nice to know about cube roots. It's the same as x cubed. Domain and range is going to be all real numbers. So let's look at some transformations, and we're looking at x cubed first. What would be the transformation that applies here? Again, I really don't like dealing with horizontal stretches and shrinks. How about let's rewrite that? Isn't that really like taking -2 cubed and x cubed? Now notice I can do that because this is multiplication inside, and exponents are repeated multiplication. -2 cubed would give me -8. So it's negative, so you have a reflection over the x-axis. And a vertical stretch by 8. On the second one, we have x plus 5 cubed. Now we know what happens when you add to the x. This is going to be translated left 5. The third one is x cubed minus 4. That's going to be down 4. Remember, it's at the end. Now this one's kind of interesting, isn't it? I don't really like that one. Let's skip that one. Let's go on to number 2. How would the cube root of x plus 3 compare with the parent cube root of x? Well, gosh, we should know this. That's going to be up 3. Just like if you'd had x cubed and you added 3 to it. So remember, we had our parent graph, went through 0, 0, 1, 1, 8, 2, -1, -1, -8, -2. Here's my parent. If I shift that up 3, every point, I'll start here at the origin, we go up 3 steps. We have the same shape. We still have negatives and positives. And even though it looks like these are leveling out, they really, really don't. They continue on and on forever. So our domain and range is still all real numbers. So think about what the transformations would be. It doesn't matter what the function is. The transformations are going to be the same. So the negative on the outside would be a reflection over the x-axis, and the x minus 3 would move it right 3. The 4 on the outside would be a vertical stretch by 4. I'm going to ignore this one. Well, we don't have to. Hold on. We can do that one. And the minus 1 at the end would be a down one. Now, I don't know why they put these two together, because these two had the same movement. This one does not. If we look at that one, it had 0.25 on the outside, and then 4x cubed, and then minus 1. Well, we could do that because we can separate that out into 4 cubed x cubed times 4 cubed x cubed. Well, that's 64. So if I take 0.25, or 1/4 of 64, I get 16 x cubed. So this one would have a vertical stretch of 16, and then it would be down 1. I don't know why they put both of those in there. All of these, what would be the domain and range? Well, the domain and range of x cubed or the cube root is always all real numbers. Negative infinity to infinity. That makes it extra nice when you're solving equations. We still want to check our answers, but we don't have to worry so much about an extraneous solution. So let's look at how we could solve a cubic. Remember, on square roots, we isolated the radical, and then we squared both sides. Well, the opposite of cube roots is to cube both sides. So watch this first example. It had 4 cube root of 2x minus 1 minus 5 equals 3. So they first started off with adding 5 to both sides. Then we still need to get the 4 away, so we divide both sides by 4. Now it's the cube root of something equals a number. If it had been the square root, we would have squared, but since this is a cube root, we're going to cube. When you cube a cube root, they undo each other because they are inverse operations, and we're left with 2x minus 1. 2 cubed is just an 8. Then it's just solving a simple equation. Let's do a couple of extra examples. Four plus, and I am going to write one in the weird form. Remember, 1/3 power really means the cube root of x minus 1. I tend to like to rewrite it. So our first step is to isolate the radical. I hope all of you decided that meant to subtract 4 from both sides. So I have the cube root of x minus 1 equals negative 2. Now that I have a radical equals a number, I'm going to do my inverse operation. So the inverse of cube root is cubing. When I cube a cube root, I just get the radicand back, what was underneath the symbol. On the other side, negative 2 cubed gives me a negative 8. Then all I have to do is add 1 to to solve the equation. If you plug that back in, you have negative 7 minus 1 is negative 8. The cube root of negative 8 is negative 2. 4 plus a negative 2 is a 2. And guess what? Since we did not have a restricted domain and not in a restricted range, do you really think we're going to have too much trouble with any extraneous solutions? No. Last example. We want to isolate the radical first. So this one's kind of easy. We got to get rid of that 7 first. We're going to divide both sides by 7. That leaves me with the cube root of 2x plus 5 equals 3. Now we need to do our inverse operation, so we're going to cube both sides. When you cube a cube root, you just get your radicand back. 3 cubed is 27. Subtract 5 and divide by 2. Plug it back in to check your answer. That would be 22 plus 5, 27. Cube root is 3. 3 times 7 is 21. So that checks. You will have a quiz on this next class, so make sure you try to practice problems in your book.